Okay, in today's lecture, we're going to cover the section 6.5 material on divergence in curl, which are two operations that we can perform on vector fields, either in the plane or in space. And we'll see throughout the remainder of chapter 6 that these divergence and curl operators have some very nice applications related to line integrals and later in the chapter 6 material to surface integrals. So let's start by defining these operations. So in general, let's suppose that we have a vector field in 3 dimensions, f of x, y, and z, whose component functions are p, q, and r of x, y, and z. So this is some vector field in space. So we would define the divergence of that vector field f as the scalar function, which is denoted as div of f, or div of f, or divergence of f. And it's defined as follows. It's the sum of the partial derivative of our first component function, p, with respect to x, the derivative of the second component function, q, with respect to y, and the partial derivative of the third component function with respect to z. So we differentiate our first component p with respect to the first variable x, our second component function q with respect to the second variable y, and our third component function r we differentiate with respect to the third variable z. And the sum of those partial derivatives is called the divergence of that vector field. Now the other operation, which we're going to talk about, is the curl of a vector field. And now the curl of a vector field is itself a vector field, which is defined as follows. So first, the notation is curl, or curl of f, and it is the vector field where the first component function is the difference in the partial derivative of r with respect to y and partial of q with respect to z. Our second component function is the difference in the partial derivative of p with respect to z and r with respect to x. And our last component is the partial derivative of q with respect to x minus the partial of p with respect to y. So one thing to make note of here in this definition is that the divergence of a vector field is a scalar function. That is a function of 3 variables, x, y, and z, which returns a number, or a scalar. However, the curl of a vector field is itself a vector field. It's a function of 3 variables, x, y, and z, which gives back a 3-dimensional vector instead of a scalar. So something to make note of there is these two operations define 2 different types of functions. Now, this definition that we just introduced for the curl of a vector field we see is a little bit messy. It might be hard to remember, but we can simplify that definition by making use of the gradient operator. So I mentioned here that the divergence and curl of a vector field can be more easily expressed in terms of the gradient operator, which we were denoting as grad or del, or nabla. It's this little upside down triangle, which is the operator, or the 3-dimensional vector function, where we are differentiating the first component with respect to x, our second component corresponds to the partial derivative with respect to y, and our third component, the partial derivative with respect to z. So these vector field operations which we're defining, divergence and curl, can be defined in terms of that gradient operator. So in particular, the divergence of f we can think of as the dot product of the gradient operator with our vector field. Let's see why that would be the case. So here we have our gradient operator del shown, and then let's think about our vector field. So here we have f, which is a 3-dimensional vector field whose component functions are p, q, and r. So one way that we could think about the divergence is as the dot product of these two vectors. So we would take the product of their first components, so that is the partial derivative with respect to x of the function p, or partial of p with respect to x, plus, then we multiply the next components, so partial derivative with respect to y of the function q, or partial of q with respect to y, and then we add the product of the last two components, so partial with respect to z of the function r, or the partial of r with respect to z. So another notation or another way we can think about divergence would be as the dot product of our vector field with the gradient operator. Now similarly, the curl of our field f we can think of as the cross product of the gradient operator with our vector field. So recall here the cross product of two vectors is defined as the determinant of a 3x3 matrix where our first row consists of the standard basis vectors I, j, and k. Our second row would contain the components of the first vector, that is the gradient operator, so these partial derivatives with respect to x, y, and z. And our last row contains the elements of the function f, or the vector f. In this case, the component functions were p, q, and r. So we see that if we were to take this cross product to get our I component, we would differentiate r with respect to y, and then subtract the partial of q with respect to z. To get our second component, the j component, we would take the partial of p with respect to z, and then subtract the partial of r with respect to x. And to get that third component, the k component, we would take the partial derivative of q with respect to x and subtract the partial derivative of p with respect to y. And so notice that this cross product that we've evaluated is exactly the same vector function or vector field that we had to define the curl of our vector field. So this cross product notation gives us a much easier way to remember how those component functions are defined. So let's look at an example of this. In our first example, we are asked to find both the divergence and curl of the following three-dimensional vector field, f of x, y, and z, whose component functions are given. So we'll start with the first one, the divergence of f, denoted as div, or divergence of our field f. And remember, we can think of this as a dot product of the gradient operator with our vector field f. So we would take our first component function and differentiate it with respect to x. So here we would have 2xyz. Then we add the derivative of our second component function with respect to y, which gives us 2 times xyz. And then we add the partial derivative of our third component function with respect to z, which would be 2 times xyz. So here, combining like terms, we have altogether 6 times xyz. So this would be the divergence of that vector field. It is a function, and it's a scalar function. For any value of x, y, and z that I plug in, I get back a number or some scalar. Now to define the curl of this field f, again, we're thinking about it as a cross product of the gradient operator with our vector field. So to find a cross product, we're looking at the determinant of this 3x3 matrix, where our first row consists of the standard basis vectors I, j, and k. Our second row consists of the gradient vector. So the components are the partial derivatives with respect to x, with respect to y, and with respect to z. And the third row of our matrix consists of the vector field f. So here our first component function was x squared yz Our second function was x, y squared z, and our third component, x, y, z squared. So let's see what we get for this vector field. To find our I component, we take the determinant of the 2x2 submatrix we get by deleting that ith row and column. So that is the partial derivative with respect to y of x, y, z squared, which gives us x, z squared. And then we subtract the partial derivative with respect to z of x, y squared z, which gives us x times y squared. Now to find our second component for this curl, that is the j component, we take the determinant of the 2x2 submatrix we get by deleting the jth row and column. So here we would have x squared times y minus y times z squared. And then for our third component function for the curl, that is the k component, we take the determinant of our 2x2 submatrix we get by deleting the kth row and column, and we're left with y squared z minus x squared times z. So we have the following for the curl of the given vector field. So here again, the curl is itself a vector field. It is a function of x, y, and z that returns a three-dimensional vector for any x, y, and z values that I substitute into it. So let's think about what these two operations might represent physically, starting with the divergence. So one way to think about the divergence is, or the most common way to think about it is the following. If we have a vector field f, which physically represents the velocity field of some fluid, then the divergence of that vector field gives a measure of the tendency of the fluid to diverge or flow out from a given point x, y, z. And here a little bit of terminology that we can introduce. In the event that the divergence of a vector field is 0, we would say that field is source-free, or sometimes called incompressible. So a visualization here to illustrate, let's consider 3 cases for divergence. So in this left-hand plot, we've got a graph of a 2-dimensional vector field, and we see that all of our vectors seem to be diverging from the origin, moving outward. So this might be a radial field. So for the origin, we see that our fluid field, or our velocity field for this fluid, is moving outward from that central point. So in this case, we would have a positive divergence at the origin. This vector field is flowing outward from the origin, so the divergence would be a measure of that tendency to flow outward. So we would have a positive divergence in that case. In this second plot, we have a velocity field that appears to be a radial field, where all of our vectors are pointing inward towards the origin. So in this example, our velocity field is not flowing out from the origin, but flowing in towards the origin. So this would be an example where we would have a negative divergence. And then the last case would be 0 divergence, or a so-called source-free or incompressible vector field. So here, if we look at the origin, our vectors may initially appear to move towards the origin before moving outward from it. And depending on what quadrant we start in, we can see that our fluid is flowing in different directions according to this velocity field. So this would be an example of a source-free vector field, or where we have zero divergence for that field at the origin. So as an example of this, let's consider the following. We're given a velocity field, f of xy, in 2 dimensions, and we're asked if this is source-free. Now, to determine whether a field is source-free, we need to look at the divergence and see whether it is 0. So here, the divergence of our vector field f, again, can be thought of as the dot product of the gradient operator with our field f. And in this example, we only have a 2-dimensional vector field. It's f of xy instead of xy and z. So in this case, our third component function, r, is 0. So we're just taking the partial derivative of our first component with respect to x and the partial of our second component, q, with respect to y. And here we had no third component function. We can think of r as being 0 here. So let's see what we have for this divergence. So partial derivative of our first component with respect to x is 2xy plus the partial derivative of this second component with respect to y gives us a negative 2xy. So the sum is 0 for any point in our field. So 0 divergence means that this vector field is source-free, or incompressible, we could say. So let's think about the other operation here. The other operation, which we were considering, was the curl of a vector field. So let's think about what it represents. So again, if we think about f as representing the velocity field of some fluid, then the curl of that field, which is itself a vector field, is a measure of the tendency of that fluid to rotate about the axis, which is defined by the curl vector, at any point x, y, z within that fluid. Now, in the case that the curl of f is the 0 vector at a point, that means that that fluid would be free of rotations at that point. And in that case, f is called irrotational. So physically here, if we have some fluid which occupies a region of space, at any point x, y, z within that fluid, the curl gives a measure of the tendency of this fluid to rotate about the axis defined by this curl vector. So here our curl vector at a point defines some vector in space given by curl of f of x, y, and z. And this curl gives a measure of the tendency of our fluid to rotate about that axis. So in fluid dynamics, we can use this curl vector to determine where we might have whirlpools within our fluid body. So let's look at an example working with the curl again. So for this next example, we have the velocity field, f of x, y, z, whose components are given. And we are asked to identify all of the points for which this field is irrotational. Now, irrotational means that the curl is 0 at that point. So we need to start by finding our curl vector. So here, the curl of f, again, is thought of as the cross product of the gradient operator with our vector field. So that is the determinant of the 3x3 matrix, whose first row consists of the standard basis vectors I, j, and k. Our second row consists of the elements of our gradient operator. So that was the partial derivative with respect to x, with respect to y, and with respect to z. And our last row for this matrix consists of the vector function f. So its component functions were x times z, x times y, and y times z. So let's see what we get for our curl vector. Our ith component would be given by z minus 0, so just z. Our j component would be given by x minus 0, so just x. And our k component is given by y minus 0. So after simplifying here, we had just z, x, and y for our curl vector. Now, in order to find points where this field is irrotational, we're going to let that curl vector, so here curl of f, which was z, x, y, be equal to the 0 vector. So in order for this curl to equal the 0 vector, we need each component to be 0. So we find here that x has to be 0, y has to be 0, and z must be 0. So there's only one point, namely the origin, where this field is irrotational. So here, let's say the only point where the field is irrotational is the origin, xyz equals 0, 0, 0. All right. So making use of this curl, we can determine for a given velocity field where this field is irrotational. So let's look at some other applications here. So one nice application of the curl vector is that it can be used to determine whether a three-dimensional vector field is conservative, making use of the following result known as the curl criterion for a conservative vector field. So recall from section 6.3, for a two-dimensional vector field, that is f of just x and y, we used the cross partials test to determine whether it was conservative. And if it is a conservative vector field, we have nice properties that we can use to evaluate line integrals of those conservative vector fields. But we did not yet have a way to test a three-dimensional vector field. So the following theorem will give us a test for whether or not a three-dimensional vector field is conservative. So here's what this result says. It says if we have a vector field f, which is continuous in space, and its curl is also continuous in space, then that vector field f is conservative if and only if the curl of the field is equal to 0. That is, if we have a irrotational field for all points in space. So as an example of this, we are asked to show that the following vector field, f of x, y, z, is conservative. And if it is conservative, that means it is the gradient field for some potential function. So we're also asked to find a potential function for that field. So as soon as we see that it is a three-dimensional vector field, if I want to show that it is conservative, the only way I have to do that is with this curl criterion. So our first step is going to be to find the curl of this vector field f, which again is the cross product of the gradient vector and our field. So here we're looking at the determinant of the 3x3 matrix, where my first row consists of the standard basis vectors I, j, and k. My second row consists of the partial derivatives with respect to x, with respect to y, and with respect to z. And my third row consists of the component functions of the field. So in this example, we had 20x cubed z plus 2y squared, 4xy, and 5x to the fourth plus 3z squared. So let's see what we have for this curl vector. So for our first component, that is our I component, we have 0 minus 0. For our j component, we have a 20x cubed minus 20x cubed. And for our k component, we have 4y minus 4y. So we see here that we are left with a vector of all zeros, or the zero vector. So if the curl of our vector field results in the zero vector, that means that this field F is conservative. So that was the first part of this problem, is to show that it is conservative. Now let's recall what that means. That means that there is some scalar function f such that the gradient of f is equal to our given vector field. So we know that since this is a three-dimensional field, the first component of that gradient vector, grad f, must be equal to the first component of our vector field. Similarly, the second component of the gradient of f, that is the partial derivative of f with respect to y, is equal to 4xy. And the third component of the gradient, which would be the partial of f with respect to z, has to equal that third component. So what we can say here is the partial of this potential function, little f, with respect to x, must be 20x cubed z plus 2y squared. The partial with respect to y must equal 4xy, and the partial with respect to z is 5x to the fourth plus 3z squared. So if we know the partial derivatives of this function, then we can find the function by taking the antiderivative of one of those partial derivatives. So in this example, let's consider f, which will be a function of x, y, and z, to be found as the antiderivative of the partial of f with respect to x. So that was 20x cubed z plus 2y squared, then integrated with respect to x. So here, finding the antiderivative with respect to x, we would have 5x to the fourth z plus 2xy squared plus some constant with respect to the variable x. Now, in this example, our function is a function of three variables, x, y, and z. We were integrating with respect to x. So a constant function with respect to x would be any function that doesn't depend on x. But it could depend on the other two variables, y and z. So this is similar to what we saw in section 6.3 when we were finding a potential function for a conservative vector field in 2 dimensions. But now, since our potential function would depend on x, y, and z, this constant function depends on y and z. Now, in order to find that constant function g, we can make use of what we know about the other partial derivatives of this function. So if we were to differentiate this with respect to y, we would have 4, or let's see, here we have a 2x times y squared. So with respect to y, we have a 4xy plus the partial derivative of g with respect to y, and that has to equal the partial derivative of f with respect to y, which we know is our second component function for our vector field, 4xy. So it follows that the partial derivative of g with respect to y is equal to 0 which means that g, which in general was a function of y and z, cannot depend on y. It has to be a constant with respect to y for this partial derivative to be 0. So if we have g of y and z and it cannot depend on the variable y, that means that it must be a function of z only. Let's call it h of z. So what we found then, so far, is that the general form for our potential function, f of x, y, z, is given by 5x to the 4th z plus 2xy squared plus g of y and z, which we just found must be a function of z only. We were calling it h of z. Now, in order to find what this h function is, we can use what we know about the partial derivative of f with respect to z. So let's look at the partial derivative of this thing. Here, the partial of f with respect to z would be given by 5x to the 4th plus h prime of z. And we know that must equal the last component of our vector field, which was 5x to the 4th plus 3z squared. So we see we can cancel the 5x to the 4th term on both sides, and we're left with h prime of z is equal to 3z squared. So h of z is then equal to z cubed plus some arbitrary constant c. Now, as we did in section 6.3, we're free, if there are no other restrictions given in the problem, we're free to choose this arbitrary constant c to be any constant that we want. So we could choose the easiest choice where we make that constant equal to 0. So finally, we find that a potential function for this field, f of x, y, and z, would be of the form 5x to the 4th z plus 2xy squared plus h of z, which was z cubed. And for these types of problems where we're asked to find a potential function, we can always check our answer because if we were to take the gradient of this answer that we find, we see that we would get back our vector field f. So we can always check our work here by finding the gradient of our answer and making sure that it is equal to the given vector field. So in our last example here, we've got a similar problem. We are considering a force field, so a vector field in 3 dimensions, representing the force acting on an object at a point x, y, z in space. And in part A of this example, we are asked to show that that field is conservative and find a potential function for that field. So as soon as we see that it is 3 dimensions, or a 3-dimensional field, we know that we have to make use of the curl criterion to show that it is conservative. So our first step here is to find the curl of this field, which is the cross product of the gradient operator with this field. So here, our first row consists of the standard basis vectors I, j, k. Our second row is the gradient operator, so the vector of partial derivatives with respect to x, y, and z. And our last row is the force field F. In this case, the components were yz, y squared plus xz, and xy. So let's see what we get for this curl vector. So here, our ith component would be given by x minus x. Our j component is y minus y, and our k component would be z minus z. So we see that we are left with the 0 vector, which means that our field is conservative. So let's start by saying that f is conservative, which means that the field f is equal to the gradient of some scalar function f called the potential, and we want to find that potential function. So, as we did in our previous example, we can define our function f of x, y, z by looking at the antiderivative of one of our component functions of the field with respect to a variable x, y, or z. So if I work with the first component function, y times z, well, I know that that must be the partial derivative of this potential function with respect to x. So I will integrate it with respect to x. And I find that we have our function is of the form x, y, z plus a constant with respect to x, which would be any function that depends on y and z only. Now to find that g function, we would look at the partial derivative of this function with respect to y, which would be given by x times z plus the partial derivative of g with respect to y, and that must equal the second component of our vector field, which was y squared plus x times z. So we can cancel the common factor x times z on both sides, and we find the partial derivative of g with respect to y is equal to y squared. So finding the antiderivative of this, we find the function g of y and z would be 1/3 y cubed for our antiderivative with respect to y, plus a constant with respect to y, which would be any function that depends only on z. Let's call it h of z. So we found thus far that the form of our potential function, f of x, y, z, is given by x, y, z plus 1/3 y cubed plus h of z. And to find this h function, we would look at the partial derivative of f with respect to z. So this gives us x times y plus h prime of z, and that must equal the third component of our vector field, which was just x times y. So canceling the common factor x times y on both sides, we find that the derivative of h is equal to 0, which implies that h, as a function of z, must be a constant. So here, if there are no other restrictions given in the problem, this arbitrary constant of integration we can set equal to 0 for simplicity. And we find that the potential function f of x, y, z would be given by x times y times z plus 1/3 y cubed plus h of z, which was any constant, we chose it to be 0. So this would be our potential function for that vector field, and we can verify that it is indeed a potential function if we work with, or if we find its gradient vector. We see that we get back the force field that we were given. Now, once we have this in part B of this example, we are asked to determine what is the work done by that force field in moving an object along the helix in space, which is defined by the vector function r of t is 3 sine of t, 3 cosine of t, 2t, where t ranges from 0 to 2 pi. So here we know that the work done by a vector field or a force field in moving an object along a given curve is found by taking the line integral of that vector field over that curve. But rather than evaluating this line integral directly, since we've shown in part A that this vector field is conservative, we can make use of the fundamental theorem for line integrals. It makes evaluating this line integral much easier. So here we would say by the fundamental theorem for line integrals. The work done by that force field is given by the line integral over that curve C of our force field F dot dr. So the fundamental theorem says that that line integral can be evaluated as the difference in the values of our potential function f at the terminal point of my curve. So that would be what I get from my vector function r when I plug in 2 pi for t, and the value of the potential function f at the initial point of my curve. That is what I get by plugging in 0 to that vector function. So let's see what we get here. Our potential function f is evaluated first at r of 2 pi. So plugging in t equals 2 pi to this vector function r, we have a first component of 0, since sine of 2 pi is 0, then 3 times cosine of 2 pi, which is 1, so leaving us 3, and then our last component would be 2 times 2 pi, so here 4 pi. And then we subtract what we get when we plug in 0 for t to our vector function. So plugging in 0 for t in this vector function r of t, which defines our curve, we have the point 0, 3, 0. So let's see what we get when we evaluate the potential function that we found from part A at this first point. The first part of it is x times y times z. Now since x is 0, we have 0 for that product. And then plus 1/3 of y cubed. So here y cubed would be 3 cubed divided by 3 gives us 3 squared, or 9. And then we are subtracting the value of our function at the other point, 0, 3, 0, which is also 9. So here we have a value of 0 for the work done by that field in moving an object along that helix. All right. So in this section, we've introduced these two operations, divergence and curl, which can act on a vector field and describe information about how this field is behaving. If we think about it, for instance, as describing the velocity field of a fluid. And then we saw that the curl of a vector field can be used to determine whether a three-dimensional vector field is conservative. And in the case that we do have a conservative vector field, we're able to find a potential function, which then allows us to make use of the fundamental theorem for line integrals. And we'll see throughout the remainder of this chapter, there are some really nice applications for these divergence and curl vectors when it relates to surface integrals, which we'll start discussing in our next